Good morning, everybody. Welcome to the Wednesday morning session of EQTC21. This is the plenary talks and panel discussion on quantum computing, quantum simulation, and hybrid HPC-QCS. The first speaker is Readiness from CNRS, and his talk is on quantum computing applications.
Thank you very much, Anthony. I want to start by thanking the organizers for inviting me here. I'm really happy to talk at this conference. I hope you are seeing my slides. So my name is Readiness. I'm a research director for CNRS based in Paris. And I'm also the head of algorithms for QCware and director of QCware France. So I would like to talk to you about quantum applications. And I guess the first question I want to ask is how do we get to these first quantum applications, right? So one thing that we know that we have to do is that we need to have the hardware manufacturers give us more qubits and better qubits, right? We are starting to see quantum machines that are able to do non-trivial things. We are not yet at the point where we have quantum hardware that we can actually provide real-world applications. So we do need better hardware. We need more qubits. We need better qubits. And this is a way to move towards these quantum applications. There is also a different way, which is also equally important. And this is by working on the algorithmic side and on the development of software side, in order to take all these quantum algorithms that we have, all these quantum applications, and figure out ways of how to make them run with much fewer qubits or being able to tolerate more noise, right? So this is also very important aspect on how to get faster, let's say, to these first quantum applications, which is improving the hardware, but at the same time, improving the algorithms in the sense of making them need less resources than the ones that we thought they needed before. Okay. So what do I mean, again, about our quantum applications and how are we going to unlock this power of quantum computers? Well, there is a big gap between the hardware and a user, right, or an enterprise user. And this gap is actually filled with software, right? So we have a layer which is called the middleware, and this is the software layer where we have all the things like operating systems and compilers and controllers and all of these things that are closely related to the hardware. And there is a second level which is closer to the users, which is the application software layer. And it's exactly these quantum algorithms in that application layer that unlock the power of the quantum computing hardware. So I'll be talking a lot about quantum algorithms, and I want to tell you why is it so important to look at quantum algorithms. The first reason is because a quantum computer is not just a faster processor, right? So it's not just a new generation of hardware that just runs whatever we used to be able to run before, just faster, right? But it's a fundamentally different way of performing computation that can be much faster for certain tasks, right? And there are some important words here that we need to pay attention. First is that indeed, it's a very different way of encoding information and of computing with this information, right? And what we know is that if we actually use this way of encoding and computing information through this quantum mechanical system, then for certain tasks, we can actually provide much faster solutions. Not for all tasks. There are many tasks where we can actually prove mathematically that the quantum computer will be exactly as powerful as a classical computer. But there are certain tasks where we know and we can prove mathematically that a quantum computer can provide solutions faster. And it's a big challenge to figure out for what other problems we can actually get such faster quantum algorithms. So I think what should be clear already now is that quantum computing will not replace classical computing, right? There are many things that we will continue to be doing with classical computers, but we do expect it to remove some computational bottlenecks and then open the way to new applications, right? And to do that, we need to rethink and reinvent new algorithmic solutions, as I was saying before. So in order to find these new algorithms, we focus on some hard computing problems. And these are hard computing problems for the HPC machines, for example, that we have today, or these are problems that we know that will hit the limit in a few years from now. So we're talking about big simulations, so in chemistry or in about molecules or for drug discovery. We're talking about machine learning where the data is becoming bigger and bigger. Monte Carlo methods for stochastic processes in applications, for example, in finance. Many different types of optimization problems. These are problems that you see a lot in manufacturing, for example, and also things like differential equations, which are important for fluid dynamics when we're talking about aerospace or automobile industry. So I put these kind of areas in some sort of timeline between things that we think that are more nearer term and things which are more medium or longer term. But as I said, this is a timeline that actually moves, and it moves the moment we find new algorithms that can actually solve these problems with a smaller number of qubits or in a way which is robust in against the noise that the qubits have. And we can start using noisy qubits instead of having to wait for fault tolerance and error correction. So what I want to do in the next few minutes is actually give you some examples for a few of these areas, like in machine learning, for finance applications, and also in optimization, of some of the work that we have been doing recently, just to get an idea of where we are right now, what can we actually do with the quantum machines that we have today, right? And what are the challenges and the prospects of doing something more interesting and coming with the real world applications in the years to come. So I want to start with quantum machine learning. This is the area that I'm spending most of my time looking at. And I think this is one of the most interesting areas for trying to actually find quantum applications. There are many reasons for that. One of the main reasons is that we actually know that if we had, big scale fault tolerant quantum computers, then we can prove mathematically that we can offer big advantages, right? That there are quantum algorithms that can provably offer advantages with respect to their classical counterparts once we have these large scale quantum computers. Here are some of the results from my recent results from my group on machine learning. We're not obviously going to go through all of this, but I wanted to show you that there is a lot of work out there, and obviously with many more researchers and many more groups in the world in all different aspects of machine learning, whether it is more on supervised or unsupervised learning, when it is about deep learning and neural networks, or more traditional methods and more interpretable type of machine learning. And this is showing that once or when, let's say, we have these big quantum computers, then we can offer a lot of enhancements and performance enhancements to classical machine learning. But we have something else which is even more interesting, or at least as equally interesting, which is the fact that we have all these different ways of trying to bring these quantum machine learning algorithms and applications closer to reality, right? And these are different ways of trying to kind of overcome these bottlenecks that we had. For example, how do we take classical data and load it into a quantum computer, right? Or how do we estimate distances between data points, which is something that we do all the time in classical machine learning? Can we do this efficiently when these data points are quantum states, for example, right? And even more interestingly, one of the main things that quantum computers can do well is actually linear algebra. And linear algebra is at the core of machine learning, whether this is something more simple like matrix multiplications, which is what you do when you are training, for example, neural networks, or when it's, let's call it more heavy duty linear algebra, things that have to do with eigenspaces and eigenvalues, and applications in machine learning like principal component analysis or dimensionality reduction techniques. Anything that has to do with this heavy duty linear algebra, a quantum computer can actually offer advantages. So as I said, what we can offer by using quantum computing in machine learning could be, for example, efficiency. We can do things faster. It could be in the accuracy, but it can also be in different elements which are becoming more and more important for machine learning, which are things like interpretability, things like trust. How do we remove biases? How do we have interpretable models? And also energy savings. So here is the first demonstration that we did a few months ago of a quantum classifier. This is a demonstration that we did with collaboration with IonQ. We looked at a very simple data set. This is the MNIST data set, right? These are handwritten digits. And we wanted to understand how well can a quantum computer that exists today, how well can it differentiate the different digits, right? So the first thing that we had to do is figure out what is the right quantum algorithm to apply to this problem and come up with some sort of quantum classification algorithm. One, we did that, and we kind of took intuition of classical classifiers and simple ones like the nearest centroid one. Once we figured out what is the right algorithm to apply, then we had to write down the software, we had to produce the circuit, we sent it to one of the quantum computers. In this case, it was the IonQ quantum computer, and we got back the results, which were the fact that for the first time, a quantum computer, a tiny quantum computer, okay, not tiny, but a small quantum computer of 11 qubits could actually, for the first time, do a 10-class classification on a quantum computer with accuracy, which is certainly not trivial. It was roughly 80%, which, as I said, it cannot compete with the best classical methods that we have, right? The ones that use GPU clusters and many other computing capabilities. But we are starting to see non-trivial things happening on the quantum computers that we have today. Okay, we have a lot of work to do to start competing with the classical things, but these are things that will be unthinkable to do a few years ago. Okay. Here is a second example where now we actually looked at the real data set, and this data set was on medical images, right? We looked both at chest X-rays, but also on retina camera images. And again, the question there is, can we do a medical diagnosis by looking at these images and figuring out, for example, if a patient has pneumonia or not from the X-ray, from the chest X-ray. So for that, again, we had to go and design specific quantum algorithms for this task, right? And here we looked at quantum neural networks, which are the kind of the analog of the classical neural networks that one uses quite commonly for things like image classification, right? We used a different quantum computer. We used the IBM, a 16-qubit IBM quantum computer. And again, what we found in the end is the fact that a quantum computer could, in some sense, offer explainable models, right, for medical diagnosis in a way which, once the quantum computer has become bigger and faster, then can actually do this classification more efficiently. Okay. So these are just two small examples of machine learning demonstrations that we did on quantum hardware. And there are many more theoretical results that show that quantum computers should be able to do many more interesting things in machine learning. And we are still, on one hand, waiting until we get more qubits and better qubits on our hands. But we are also trying, and this is very important, is to figure out how to take this algorithm from using thousands of qubits to being able to use hundreds of qubits, for example, and still be able to be very performant. So let me go now to quantum finance, and the application I want to show you here is some work that we did with Goldman Sachs, where we looked at one of the canonical and fundamental quantum algorithms, the one that is called amplitude estimation. This is kind of the basis for things like Grover search, right? And the question is, can we use this algorithm for doing some quantum Monte Carlo methods, for example, for finance? Okay, so this is something that has many applications in derivative pricing, risk analysis. So we kind of know what Monte Carlo methods mean. Basically, you have some process. It could be the stock market. You want to compute something, some expectation. And what we know is that basically, if you want to compute this value, which could be like the price of this asset with some good accuracies, let's say some accuracy epsilon, then we need to run this stochastic model, this market, many times. And we know from mathematical proofs that one needs 1 over epsilon square runs of the model in order to get to some good accuracy. So what this quantum algorithm, this amplitude estimation algorithm, says that if I can use actually a quantum computer, then we can save a lot on the number of times that we need to run this model, and we can get the same accuracy as the classical one with only 1 over epsilon runs. right? And the difference between this 1 over epsilon and 1 over epsilon square is going from millions of runs of the model that we have to do classically to thousands of runs that we have to do on a quantum computer. So in theory, this says that if we are able to run this quantum algorithm, we could be looking at 1,000-fold speedups in all these processes that happen very, very often and every day, let's say, in the financial institutions. There is, of course, a caveat, and the caveat is that there is a main bottleneck for this algorithm, which is that this algorithm needs very, very high quality qubits. And the reason is that these circuits that we need to apply are very, very deep somehow. So what do we do? So as I said, we can either wait until the hardware becomes much, much better, and then we have to wait many, many years. Or we can try to figure out how to improve the algorithms and make them work with machines that we hopefully will start to see sooner than these 10+ years, right? So we devised exactly this new type of Monte Carlo algorithms that we call them low-depth algorithms, right? With our methods, we can obtain speedups with much lower depth quantum circuits, okay? We can tolerate several orders of magnitudes more noise. And of course, we have to trade off some of the speedup with this noise tolerance, right? So if we want to see some numbers, what we knew before our work is that the quality of the qubits that we would need in order to be able to price, for example, some simple derivatives or moderately complex derivative would be something like we needed to have less than 1 error in 10 to the 9 operations, right? And if you talk to experimentalists and say, I need to be able to do 10 to the 9 gates without having any error, then, you know, they kind of say this is really not for today, not even for the next 5 years. So what we managed to do with these new algorithms is that we managed to reduce, you know, the quality of the qubits that we need, all by 3 to 4 orders of magnitude, right, to something like 10 to the -5, meaning that one needs to do something like 100,000 operations. Again, this is not possible to do today, right? Even if we look at the best current error rates, then we have something like 10 to the -3. But we managed to go from 7 orders of magnitude away from being able to run this algorithm to 2 orders of magnitude away to start seeing this algorithm actually being able to run in some real use case that comes from finance, for example. Okay. We went one step further and said, can we implement something today? Can we demonstrate at least that this algorithm works? And for that, again, we needed to use 2 very important ingredients. We needed to use these novel algorithms that actually use these low depth circuits, and we needed to use the state-of-the-art hardware that we could find, right? If we were trying to use the old algorithms in the state-of-the-art hardware, we wouldn't be able to do it. If we would want to use the new algorithms in the older generation hardware, we wouldn't be able to do it. But combining the best of the algorithms and the best of the hardware, we managed to get some very good results. And all I want to show you is that you can see that the orange line, which is this new quantum algorithm, can get an error which is much, much lower than the blue line, which is what the classical Monte Carlo method would be getting. So optimization, we have different ways of optimization. I don't want to say much. It's just that it's a very interesting area. There, the issue is that we work a lot with heuristics and not algorithms, meaning that we cannot prove that things will always work. But this is also how we work classically for optimization problems. We use classical heuristics, and we need to know how these heuristics work. So we need hardware to be able to run and test and change the heuristics and make them better. And I want to finish with my last slide to come back to some prospects and challenges. I hope I showed you a few kind of powerful tools that we have, whether they have to do with linear algebra or Monte Carlo methods or optimization. They're very subtle. We need to be very careful how we use these things, right? It is not easy to come up with quantum algorithms. It takes a lot of expertise and experience in doing these things. That's why we don't have that many algorithms, quantum algorithms out there, right? We saw some promising research directions, whether it is in machine learning, in Monte Carlo, or in optimization. And the last comment I wanted to make is that I think that quantum computing, you know, I think the goal that we need to have, at least in the flagship, is that we need to find practical solutions to real world problems. This is the only way that I think all this kind of funding that we are getting is justified if we're really trying to make the world a better place by solving some problems that exist out there. And for that, we need to applications. And of course, let's continue to build the hardware, and let's build the hardware that we need in order to be able to run these applications and provide real solutions to real world problems. So thank you very much.
Jordanis, thank you very much. That was a fascinating talk. To the audience, yeah, please feel free to use the chat function to ask questions. We don't have much time, so I'll just pick one from David Shaw from Fact-Based Insight. So he says there are well-known examples where algorithms have been dequantized to inspire better versions of classical algorithms. What is the latest insight on how the polynomial runtimes of these new classical algorithms compare with the quantum algorithms?
Mm-hmm. Yeah. So to be very honest, my ultimate goal is to solve problems that we cannot solve today. If we find a quantum algorithm to do it, this is great. If once we find the quantum algorithm, we get an intuition and we go back and we find a better classical algorithm, this is also great. What happened recently with machine learning is that there were these dequantized algorithms that took intuition from the quantum algorithms. There is still a very big difference, polynomial difference, on the running time of the classical and the quantum case. And the quantum algorithms, in theory, are still many orders of magnitude faster, or they will be faster when we have the hardware, than the dequantized classical ones. So I still think that the dequantized algorithms are great to have, but we still have a very good chance that the quantum algorithms will be much faster once the algorithms and the hardware meet at some point, hopefully soon.
Awesome. Thanks very much, Jordanis.
Thanks
so
a lot.
that's our next speaker, Francesco Veleno, who is speaking about extended quantum simulation. Please take it away, Francesco.
Thanks a lot. 1 second. Yes. I hope you see my screen. Okay, great. It's a great pleasure to be here today and to be part of this exciting session for me. So I would like today to try to, let's say, share some of the direction where quantum simulation with ultra-cold atom might go, and it's going in the last year. And I think here the key word that we would like to have is this idea of extended. Let's say to try to create quantum simulators which are actually pretty big with many particles or many constituents, and that has additional very high connectivity. And so just to recap a little bit of the key concepts that are fascinating us for quantum simulation. So the general question that is very well known is when you want to study the behavior of one quantum system that at the end is very complicated. The idea of quantum simulation hold on the idea on the basis of finding a different quantum system much easier. Of course, I mean, this sentence, it looked like there is something tricky behind, because how it's possible that something much easier can actually map out the behavior of something extremely complicated. I mean, in classical life, I don't know how many of such examples we would find actually. But the point is that quantum mechanics is highly universal. So this huge universality also means that systems which have a completely different microscopic behavior and let's say really the ab initio, the microscopic force between constituents of matter can have very different strengths and can operate and be active at very different scale. But still, if one system would obey to the same equation and the same Hamiltonian of the initial complicated state, the result, the solution would be universally understandable, both considered the complicated initial state or the much easier one. Of course, you can look at this type of connection between, let's say, initial system and equation of state or a Hamiltonian as a little exercise, no? But the real challenge is to find the physical relevant problems, the physical relevant question, and the physical relevant application. Because this type of connection can be also trivially, let's say, applied to some system which is not very relevant. Now, I like a little joke that a colleague of me was sharing, and I mean, let's say our psychological sort of point of view about quantum simulation, which I find very nice. So let's say that you have a quantum system which is complicated, like this dragon that is, let's say, emitting fire, and this is our target. We want to understand something complicated, is difficult to catch, is difficult to observe, is even dangerous in this case. And then we try in the quantum simulation to get, let's say, a proposal, a model, and to put together ingredient which all together might have the same type of equation. So we would, okay, as a dragon, let's take, let's say, first the body of the dragon, and then let's take it the wings, and then finally we have the corn, and those are our ingredients that we put together. And then what we would do, we would try, let's say, to study a model system which is not the same, but it's quite similar and might follow exactly the same rules. Of course, this is just a joke, but the real physical questions that we would like to ask ourselves are now becoming more and more as here and understanding are progressing. So the original motivation were to study simply conductivity, electron motion into a metal. So how the electron are let's say, conducting, localizing or delocalizing in different crystalline structure, and the quantums, and one of the pioneer results with ultra cold atom was really to put these atoms, which are extremely well controlled, in a lattice. Of course, from here you can go in more complex system, try to study the superconductivity, simulate this physics with ultra cold fermions like electron, try to understand the mechanism of pairing between electrons. So all these are very special physical relevant problem, and so with quantum simulator we get a very, very high precision and understanding of the system, and more you can start to see this type of quantum simulator as a special purpose quantum computer. So what is also important to say is what are the key ingredients we have in our lab, and the crystal of light that we can call optical lattice is certainly one of these. So, I mean, nowadays technology is progressing enormously with laser technology, optical technology, so you can have really a lattice, almost perfect, made of light, and you can pin and organize the atom in each of these lattice sites. And now you don't need to have just few atoms, you can have 10,000 atoms, each very well localized. And now this atom can interact between them, and as soon you switch on and interact on this huge amount of particles, so it's extremely hard to make a physical prediction. And the computing time to get out the solution, which can be the lower energy of the system, or it can be quantum mechanically the Hamiltonian problem, is can growing exponentially with the volume of the size. And this is now the idea why we take this model that we control and we study model Hamiltonian. So we think we know the Hamiltonian of the system, and we try to verify this Hamiltonian using the experiment, and to then get the physical law of interest. And one of the main examples that by now extremely known is the observation of the superfluid to Mott insulator transition, which is really a purely quantum stating, which come out from the interplay between tunneling and some on-site interaction. This type of Mott insulator are now used as a starting point for much more complex physics. And there is a very nice paper recently also in this analog quantum chemistry simulation. And this was kind of the starting, the most easy point, take atom, pin it in a very regular lattice. But I mean, of course, now the optical technology gives us the possibility to engineer almost any geometry of lattice. So we can have geometry which are relevant in solid state, let's say like graphene geometry, and try to engineer interaction between them. And another very important tool, which really was revolutionary also, it's the, let's say, the possibility to observe each atom and with the so-called quantum gas microscope. And now there is also a very nice review article out about quantum gas microscope. Of course, from the detection is just a very small step to go to local control. I mean, you have an objective which is extremely high resolution, and you can really project any type of little tweezer that allows you locally to imprint the excitation that you want, or locally to make a readout of your slit. And now all this idea from the original Motti and superfluid to Motti insulator demonstration, all this new tool goes together with a lot of novel theoretical model, and all together are going really into the direction of example which can simply not be simulated in a classical computer. And this is really happening, and I want to give you an example of one result from the group of Marcus Greiner in Harvard, where many of these ingredients that I was telling you were putting together. So there is the lattice, there is the fermionic statistic, there is the use of a very specific optical tool to engineer the entropy, because of course what is the key point of all this quantum simulation is that you want to have an extremely low entropy state, such that, I mean, the thermal noise, meaning the thermal excitation, don't play an important role. And you can reach really fundamental phase of matter that otherwise would be completely covered or scrambled by thermal excitation. And so he did the entropy engineering using what is called the DMD, which is a new tool of local control. It's a device made of micro mirror, and you can control each of these mirrors, putting in on or off configuration. He had a microscope, and when you put all this technology together, you start to have an enormous controllability. So you go from the traditional quantum simulator to more and more programmable quantum simulator. And now in this specific example, he was able to, this group was able to observe really long-range antiferromagnetism in fermions, with a system of a substantial high number of interacting particles. And of course, I mean, here, one key point that we have to think is the potential that are confining this atom. So we have here a lattice, and many of these quantum simulations have been done with lattice. Now, the lattice is really very nice to contain many atoms, but on the other hand, you can certainly put a local tunability like an optical finger and do many things, but it's hard to move the lattice side. So you can globally have a type of an accordion where, let's say, the lattice spacing can be changed, but it's very hard to move one lattice side around. And so let's say a complementary approach, but which is now, let's say, touching lattice, is the approach of having the so-called optical tweezer. Now, these optical tweezers are not done by, let's say, few laser light. Any point here that you see, and this is a very beautiful result from the group of Antoine Gravier, every single point is an independent or controlled micro trap made of light. And in each of these microtraps, you can have a single atom, and you can move around the atom. What does it mean? It's not only fun, which certainly it is, but it's also that as soon as you try to load this microtrap, maybe hundreds of microtraps, and you have some imperfection in your loading, you can reorganize this trap, get rid of the imperfection. Imperfection means entropy. So it's a very, let's say, it's a geometrical way to engineer entropy and get rid of any vacancy. And this is extremely interesting. And so, as you can see, all about here is about giving more programmability. And so I think that what we are seeing in our community of atomic quantum simulator is really a narrowing of the watershed between, let's say, quantum simulator and quantum computer. Because a quantum simulator, we are starting really to learn how to program, how to control atoms, how to assemble one by one our simulator. A key point for quantum simulator is that we have an ensemble of atoms. We kind of almost throw this atom in a, let's say, potential, and then we make them interacting how we want. However, the way we would like them to interact strongly depend on something which is not universal, meaning the nature itself of the atomic physics of the atom you are considering. So we are having, I mean, it's a continuous interface between having universal quantum platform, but on the other hand, using a specific atomic species, which has his specific microscopic potential. And many of the quantum simulation which is going on now, actually the most advanced protocol of quantum simulator are done with single valence electron, like alkali atom. And as well, if you look at the Tweezer array, as well, alkali is the main workhorse for all the beautiful results. So the technology, the manipulation technology with alkali is extremely developed and allows us to go in this fantastic direction. Now there is a little twist coming about a few years ago, especially in the United States, using not only one electron atom, like alkali, very simple, but using, let's say, 2 electron atoms with strontium. And I think that now it's kind of fair to say that the United States has an important leadership, and in particular GILA, about having strontium atom. The best sensing clock existing is done with ultra cold strontium atom back in GILA. But already the addition of 1 electron more at the microscopic level open, let's say, a kind of really huge new possibility. And now what is another direction where I think Europe has really a leadership is not having 2 electron atoms, but to kind of go to many electron atoms. And these are the atoms which are of interest in many labs at the moment, which are belonging to the lanthanide series. Indeed, there is a lot of space in the table of the periodic elements, and each of the atoms give us some specific enhanced capability. And just to give you an example, a few of the strengths of going from 1 to 2 to many valence electron atom. So you can, first of all, this many electron means extremely rich internal structure of the energy level. So you can have a huge reservoir of internal degree of freedom. Then you have special type of manipulation controlling transition. These atoms, so while the huge internal degree of freedom are very interesting for storing information, these atoms also have specific transition, which are extremely narrow, Locke-type transition. And the interesting things is that from the ground state, they have a Locke transition at the telecom wavelengths, which would be really interesting to think about in terms of quantum network. And another point is that when you then start to go to the Rydberg physics, all these many electrons means that your Rydberg atom, together with its core, has a huge atomic polarizability. It's extremely optically active, opening new way of optical control of Rydberg atom into tweezer. And of course, probably the most speaking properties is the very large magnetic moment. And now, if you have a very large magnetic moment, and the erbium and dysprosium are indeed lanthanide, which are among the most periodic atomic, most magnetic atomic species, then there are a lot that can be done. And just to give you an example, this strong dipole moment means that there is a long-range dipole-dipole interaction between the atoms. And so suddenly you have, let's say, a nearest neighbor interaction, but you can also have various next nearest neighbor interaction, and every atom almost let's say, interact with any other atom into the system. It's an extremely long-range type of behavior which you can control by the geometry of your lattice. And so suddenly you can have this quantum simulator which have a very high connectivity, very complex entanglement properties. And for example, one can observe as a model Hamiltonian and study the Bose-Hubbard. And first you have to verify that this is a good Hamiltonian, but now there are new protocols in which you might ask what is the Hamiltonian you should learn in this very complex, highly connected quantum simulator. And so you can create a, let's say, really type of different dynamics where the atoms are very highly, let's say, interacting between neighboring sites, but you can also say in the lanthanide type of atom, let's use the internal degree of freedom of the atom, because as I was mentioning before, lanthanide and in general multi-electron atom have a huge storing reservoir of internal degree of freedom. So you are making really the step into a complexity which open new door. And so this many internal degree of freedom you can see as a many spin state, and suddenly you can really try to simulate in synthetic dimension, where the synthetic means the spin, a lot of different type of long-range interactive lattice spin model, which are I mean, among a system with very, very open and mysterious questions to be still understood. Of course, since you have atom, and contrary to ion, for example, you can even study the transport very easily. So really of the external degree of freedom, as well the transport of the internal degree of freedom. And so, for example, the long-range spin interaction that you would have is an interaction that are connecting two different spin states in the sense of two different degrees of freedom. You can simulate Heisenberg model where now the Hilbert space is really huge. And this is just an example. You can go much farther, and yeah. And so this, of course, you can do with several long-range interacting atoms, and we have done it, and a lot of research is done with highly magnetic atoms because they combine long-range and connectivity together with the easy way of manipulating. And so here is an example of another model, Hamiltonian, where you have inside interaction, spin exchange interaction, then the next step you can even look at the transport. So I think now my time is over, and I would like just to tell you that there are many different features of this multi-electron atom we are about to discover. I mean, it's a very new field, and if you would like to learn more of the special feature, there is now a special issue, a kind of small review in Nature Physics highlighting the properties. With this, I would like to thank you for your attention.
Thank you very much, Francesca. Very interesting. We've got time for a quick question from the chat from Peter Lemeka, who is asking, where do quantum annealers belong? Would you classify them as quantum simulators or quantum computers?
Yeah, as I was mentioning, for me, from the point of view also, I would say of Innsbruck, where we have a lot of, let's say, quantum computing, quantum simulation things, I would say it starts to become difficult to classify this type of device where you have very high programmability. I mean, we really are moving toward an extremely high programmability. There are many different ideas of doing protocol. We start to have this variational approach for quantum simulation. We start to develop a Hamiltonian learning approach. So the watershed, in my opinion, it's kind of narrowing enormously, and this is really the interesting side of the recent development.
Great, thank you, Francesca. All right, and to our third and final speaker before the panel session, Crystal Mikkelsen, who is speaking about HPC-QCS infrastructures pave the way for practical quantum computing. Over to you, Crystal.
Thank you very much, Anthony. So first of all, I would like to thank the organizers for inviting me to present our work on these HPC-QCS infrastructures and some of the applications that we have. So, as you all know, we have many different communities in high-performance computing, and they come from science and industry. This is a diverse user group, and they have various hard computational challenges to unravel complex systems. Now, with the quantum computers, there is the hope that they can carry out some of these calculations, which are really difficult for the HPC systems. And one can think of quantum simulations with applications in quantum chemistry. Another class of problems that quantum computers are hoped to be of great help are the optimization problems. And as the optimization problems are a part of machine learning, a third class of application is also quantum machine learning. In the meantime, we have a large variety of quantum computing, I would say, platforms with different types of qubits. We have ion-trapped qubits, we have the superconducting qubits, we have molecular spin qubits, we also have seen, we have the neutral atoms, and so on. So a few years ago, Thomas Lippert and I decided maybe we have to come up with the quantum technology readiness levels scheme, which describes the maturity of this quantum computing technology. And this is similar to what NASA has for their tools. So we also introduced 9 levels. And if we have some systems in the laboratories, usually university laboratories or of research organizations, they are often looking at maybe the more exotic qubits, and they only have a few. The quality is not always so high. Small systems, definitely no error correction. So then we say they have maybe a level 2 or 3. If we go to the commercial ones, like we have the ones of IBM or Rigetti Computing, IonQ, EQT, then we have some qubits with higher quality. The systems are also bigger, but the systems are still too small to have error correction. So we cannot speak about universal quantum computing. Then we also have the quantum annealer of D-Wave commercial version with superconducting qubits. And this is a different type of quantum computer, but nevertheless, one can also use this scheme here. And on this scheme, we would say this quantum annealer can have a level of 8. And this is because every 2 years, the size of this quantum processing unit doubles. And this makes that it's already useful to study prototype applications. But nevertheless, we can say that here we have a huge challenge and opportunity for practical quantum computing. So we have to develop for these devices prototype applications and use cases. And we do this for, or we have to do this for all different types of devices. So for quantum simulators, the quantum computers, and the quantum annealers. Now, in our vision, the high-performance computers and the quantum computers have to be linked to solve problems optimally. So at the moment, we have here at the left-hand side the high-performance computers, and they are very useful to emulate these quantum computing, simulating, and annealing devices. This helps us to understand how these devices operate. Maybe we can help with these emulations in the design of these devices, and definitely it's of very big use that we can use this HPC system in the cross-platform benchmarking of the quantum computing devices. But the ultimate goal is to connect these two types of computers to come to hybrid HPC quantum computing simulations for real-world applications. So on the one hand, we have the HPC systems, and on the other hand, we have this large collection of quantum computers and simulators, and we have to connect them. So for the software point for this integration, we can rely on our knowledge of the HPC EQ system. There we have three ingredients. So of course we have the hardware, we also have the software, and then the third one are the users and their applications. So we can use the same ingredients for this integration. Then in the intersection of the software and the users and their applications, we see that we will have to develop new algorithms and software. On the intersection between software and hardware, we have to come up with the QCS full software stack. And on the intersection between the hardware and the users, we have to benefit from a co-design process to develop use cases, relevant use cases. So we have to hybridize these quantum and classical computing systems, and with this, we then are sure that we can come to the full potential of quantum computing. We already know some hybrid quantum classical algorithms. These are the variational quantum eigensolver, or VQE in short, which we can use for problems in quantum chemistry. We have the quantum approximate optimization algorithm, in short QAOA, which we can use for different kinds of optimization problems. And then, for example, we also have the quantum support vector machine, which one can use in machine learning for classification and clustering of data. So, of course, one has to, in order to develop these algorithms further, we have to do a proper benchmarking and a real implementation on the real quantum computing devices. If we come to the hardware and then the hybrid quantum classical hardware, there are in big lines two ways to connect the conventional computers with the quantum computers. One can either go to some form of cloud access, or one can go to a deep integration of both types of computers. If one makes this connection, then one has to take care of latencies and execution times. Maybe not in the beginning, because we are in the learning stage, but definitely for production runs, we have to. Now, me give you an example of an application. And for this, I will give you a use case where we used the quantum approximate optimization algorithm and also quantum annealing for the benchmarking. For the QAOA, we used the Euler Universal Quantum Computer Simulator to simulate QAOA on a Euler supercomputer. Now, QAOA, as I already mentioned, is a variational quantum algorithm. It's a hybrid algorithm, and it relies on an iterative process where we have a quantum part and a classical part. In the quantum part, one has to measure the resulting state of a quantum system and evaluate its energy expectation value. on the classical part of the algorithm, we have to carry out an optimization algorithm, and this is used to optimize vectors of two vectors of parameters of unitary transformations which are used in this energy calculation. So what we did is, for the execution of the quantum part, we used the GPUs of our Joule's booster. So the GPUs play, in this case, the role of quantum processing units. For the classical part of the algorithm, we used the CPUs of the same system. And as an application, we looked at the simplified tail assignment problem for 40 qubits. This is an application from the airline industry. It's an optimization problem where one has to take into account all kinds of constraints. Now, of course, quantum computers are small. We can also simulate exactly only small quantum computers. So we have to simplify these real world problems. And we did this for a 40 qubit case. So if you're interested, you have some literature here, and there is also a small movie that we made for this application. Now in Jülich, we have for our supercomputing system what is called a modular supercomputing architecture. This means that our supercomputer system consists of different modules. We have a module consisting of the cluster. This is a system with mainly CPUs. We also have a booster, a system with mainly GPUs. And then there are other modules foreseen for data analytics, storage, and so on, but also the more exotic ones for future computing. And here you see that there is a quantum module. What we did for this Quioa simulation is we used the booster for doing the optimization on its CPUs, and the quantum circuit was simulated using the GPUs. What we could do is use, for example, the CPUs of the cluster module, and if we have this quantum module, run the quantum circuit on one of the real quantum devices, quantum computing devices. So let us have a more deep look into this quantum module. As I said, the plan is to have a seamless quantum computing HPC integration with the perspective of carrying out quantum classical hybrid computing models in an efficient way. Now, in this quantum module, or very closely connected to it, we have the Jülich Unified Infrastructure for Quantum Computing. This is a quantum computing user facility for researchers, European researchers in academia and industry. In Unique, we install, operate, and procure various quantum computing systems. We provide our users with a unified portal for access to quantum computer emulators, and these are the Jülich Unified Universal Quantum Computer Simulator and an Atos quantum learning machine, and then various quantum computing devices which are at different levels of technological maturity. Now, what you see here is not all what we have, but many of these things are in the planning. What we have is we have cloud access to the quantum computing device of the OpenSuperQ project. It's a quantum flagship project in which a quantum computer is developed with superconducting qubits. Then we have a national program providing cloud access to a digital analog quantum computer of IQM. There will be an HPC quantum simulator project about which I will tell you a little bit more in a few minutes, and we will provide access to a D-Wave quantum annealer. Now, in the strategic research agenda of the quantum flagship, it is mentioned that a goal is to come this quantum computing and simulation infrastructure. Now, in 2021, Euro-HPC joint undertaking supports the first hybrid HPC quantum computing infrastructure in Europe. And this is exactly this project which I was talking about. So it's high performance computer and quantum simulator hybrids, that's the name of the project. Here you see the partners that involved, and I would like to tell you, please stay tuned for the press release because this will appear in a few minutes. The project is officially starting today. So, and with this slide here, I would like to conclude by saying that the hybrid usage of high performance and quantum computers will be the key to a successful development of quantum computing applications. Thank you very much.
Thank you, Crystal. That was really interesting. One question I had, I was interested to see your hierarchy of quantum TRL levels, which I hadn't seen before. Do you think that those TRL levels are kind of equally spaced in terms of difficulty, or is it harder to get from a particular, say, to get to the error correction quantum TRL level? Is that the most difficult TRL level to jump to?
Yes, I would say this is definitely not equally spaced. Maybe at the bottom, it's rather equally spaced, but if for these gate-based quantum computers, we have to go to the error correction. That's a huge gap because we need to implement this error correction, and in order to do this, we already need a large number of qubits, which are of high quality.
I see. One question just come in from the chat from Ivan Wojkov, asking about the JUNIC. Would it be an open access platform / service?
Yes, so the idea is that it will be possible that you write a proposal to get access to the device, and then it depends whether you are a member of the academic community or the industrial community. As long as industry partners are involved in a research project, then they can have access to the devices. If it's really an industry customer, then it depends on the contracts that we have with our hardware suppliers. But yes, it will be peer-reviewed open access.
Great, thank you. So should we all turn our cameras on and start the panel session? Great. So I've got two questions that have come in from in the chat. The first one from Eduardo Beatty, who is asking, quantum advantage has been demonstrated in application-specific quantum machines such as boson samplers. Do you foresee new application-specific machines offering a quantum advantage for real-world applications before general-purpose quantum computers are able to do so? Yanis, maybe I'll put that one to you.
Yeah, it's really a very interesting question, and it's something that we have been starting to think very carefully on. You know, what I was saying. The goal of the community should not be to build the hardware. The goal is to solve problems, right? And for that, we need to build the hardware that actually is useful to solve problems. So not the hardware that it makes sense to build in the lab somehow. So I think indeed that we need to understand what problems do we want to solve and what is the best hardware for that. A universal quantum computer is great, right? but the universal quantum computer that is built on a grid connectivity, to me, doesn't make much sense, because I don't know any algorithm where this grid connectivity is actually useful, right? For example, I would be much happier to have a line of qubits with some long range things than a grid, for example. I understand that some things are simpler on the lab than others, but that's why we need to discuss together, right? We have algorithms that we're trying to use the hardware. If we're building the hardware that is not done for the algorithms, then it would just take much longer and many more years and much more frustration in order to actually figure out how to solve problems. So I do believe in specialized hardware, right, that will have the connectivity that we need for the algorithms, that will have very good gate fidelity for specific gates that we need. I don't care about all possible gates. I use specific gates. If you can do these ones well, then I'm happy, right? So yes, I do believe that both for chemistry simulations and for machine learning, specialized hardware, which is not the ones that we're trying to build now for a universal quantum computer, could be much more helpful to us and will get the timeline shorter.
Well, Dennis, do you see error correction working in the same way on special purpose devices, or so not necessarily analog simulators, but digital quantum computers, but for specific applications? Would that kind of cut down the overhead in error correction protocols as well if they're special purpose?
I think so too, because if we know exactly the structure, the architecture of the circuit that we're trying to implement, right? If we know where we're applying the gates and what kind of errors are more harmful than others, then we will try to make error correcting codes which are tailor-made for the specific circuits, for the specific algorithm, and they don't have to be necessarily the best error correcting codes for everything you want to build. They have to be the best for what we're trying to solve, right? So I also think that error correcting code should be something which is tailor-made together with what is the algorithm that we're trying to solve, what is the hardware that we have. And this is, look at what happened with machine learning, for example, right? The algorithms were there in the 80s, in the 90s, the theory was there. Why are we talking about machine learning today? Because GPUs happened, right? This is a very specialized hardware that was made because we knew what we wanted to implement. We knew that we had to do linear algebra fast, and we created the GPUs to unlock the power of machine learning, right? We do have some applications that we know that quantum computers are good at. Let's look at them and figure out what's the right hardware for them.
Great, thanks, Dennis. Francesco, so sort of the same question to you, but maybe in the context of cold atoms, which is sort of famous for simulating condensed matter systems, but also some of the problems that you highlighted in your talk. I mean, how do you see error correction working in those kinds of simulators?
Yeah, I mean, I think that it's, so as first reaction, I would say probably there is not a universal answer to this question, but somehow it's certainly less, so it's less fragile, or it's less needed. In some sense, just really from the point of view, it's much more quantum computation that you kind of have the error correction. A part of the protocol itself is the error correction, as for example in these recent ion papers that we get from Innsbruck as well. And for quantum simulation is actually probably most kind of less central, is a less central topic, but maybe a point which is kind of a little bit of a shift of point of view now with the quantum advantage and where do we go and which problem can we solve. I think in quantum simulation there is a very specific trend over the last years which is shifting a little bit the point of view. So we are always saying, I know the problem, which quantum mechanically means I know the Hamiltonian, and now I solve it, and now I want to solve it better than computer, or I want to solve it better than other platform. But I think that quantum simulation is a very good platform to change the question and say, what is the Hamiltonian? And this is the point where we kind of are now. in the sense that who tells you that the Hamiltonian, that the model Hamiltonian, so how much the system itself can teach you on the real Hamiltonian. So there are certainly high order correlation that you are forgetting in terms of entanglement. There is the purely fluctuation of interacting many-body system coming from entanglement. Who is telling you that the algorithm that you want to impose for quantum solution is the right one? And this is all the full, let's say, direction of Hamiltonian learning, which is completely, I mean, it's a completely different point of view. You don't need to, let's say, certify your result or your quantum advantage. You ask even before whether the equation, the law governing a physical problem are the right one that you think. So that's, for example, something very handful in quantum simulation.
Thanks, Francesco. Crystal, I think you touched on this in your talk, but in this infrastructure, this HPC-QCS infrastructure, how strongly do you see the role of application-specific quantum modules?
Yes, as you can see from this picture that I have shown you, we are looking at different platforms. And this is exactly the reason. Each platform has its advantages and disadvantages. And we also don't see that in the near future, we will have a universal quantum computer. So we see this more as special purpose devices. And therefore we want to have different, we use ourselves different types of quantum computing platforms. And we also want to provide this to our users. So therefore we want to have these quantum simulators, these gate-based quantum computers and the quantum annealers in there, so that we really can perform cross-platform benchmarking.
And then on the topic of benchmarking, a question from David Shaw from Fact-Based Insight. What are the most useful metrics to compare gate model quantum computers, quantum simulators? And what lessons on metrics can we draw from high-performance computing? I'll put that one to you again, Crystal.
Yes, from a theoretical point of view, we all know there are different metrics. So one can look at the number of qubits. We have these quantum volumes and things like that. Coherence time of the qubits. But as I would say, someone who's looking at practical quantum computing, I must say that unfortunately, we have the experience, if we look into these quantum algorithms, we do not yet really have a real metric. So whether we have an example where a gate-based quantum computer can have the worst quality with respect to coherence time of the qubits, the gate fidelity, the fidelity of the qubits, and nevertheless, this quantum computing device can give a better result for a quantum algorithm than the one that has the best theoretical quality. So we, from the practical side, are still wondering what is the best metrics there. And therefore, we always look into this benchmarking and simply look at the outcome.
Thank you. And you were on the famous result from Google that demonstrated a quantum supremacy a couple of years ago. I just wondered, how do you feel about the latest device from IBM, the Eagle 127 qubit processor, and are you excited by its quantum volume or reported quantum volume? Which I don't have that figure in my head, but I think it's impressive nonetheless.
Yes, so as I said, I come from the practical side. Then I want to test these devices. These metrics are, of course, based on measured outcomes. But I want to see what they do for a real quantum algorithm. And of course, the one of Google that we use there for benchmarking, it's a quantum algorithm. It's not one that has a practical application, but nevertheless, in that sense, it was a milestone. Here with IBM, as I said, I want to test it. but for me, it's no guarantee, given these quantum volumes and so on, that it's also good for practical quantum algorithms. And this is also something which we see in the literature. We see the number of qubits increasing, we see the quantum volume increasing, but if we look then at the quantum algorithms or applications that run on these devices, they usually only use a small part of the qubits. So the question is why?
Connectivity?
Maybe, yeah. Can be.
Thanks.
So, but this is then also a parameter which has to be taken into account for
It's
your
also
applications.
noise. It's the thing is that when you have a specific application, then the moment you want to fit a bigger problem and you increase the number of qubits, you also increase the number of gates that you have to apply somehow, right? And I think this is the problem. The problem is not that you cannot use 16 qubits or 27 qubits. But if you want to really do something useful with 27 qubits, then you need more gates than what you use with 4 qubits or 8 qubits. And this is when you start getting noise at the end, right? Like on my side, the largest number of qubits where I managed to do something interesting at the end was 8 qubits. Because once you go, even on a 16 qubit machine, because the moment you go to more qubits, then the algorithm needs more gates, and then the fidelity of the qubit is not good enough, right? And that's why it's interesting to look at on the application side and say, here are some challenges, here are some algorithms, run them on your computer and tell me what results you get, right? To me, this is what I care about. It could be a combination of the connectivity, the fidelity, the T1, the T2, all these are great while you're building the machines, but the goal of the machine is to solve a problem. So let's see what problems they can solve and for what kind of, dimensions and all of this. So we will be getting there. The machines are very small. I mean, it's extremely impressive what's happening on the hardware side. I don't want to I mean, it's really, really amazing. And we need much better hardware and we need much better algorithms. So, we'll get there. It will take some effort.
Time for just one more question, I think, just to get the quick thoughts from the panel on how the Flagship is doing, and maybe should any directions be changed in the light of results in recent years from around the world, from China and the US on quantum advantage and quantum supremacies and so on. For Francesca, maybe I'll put that one to you first.
Yeah, okay. I think that on the one hand, this question is clearly that everybody would see more on his own field of research, but there are a lot of discussion within the quantum simulation community, really enormous, very deep discussion about what is the role of the quantum flagship for quantum simulation, how much is represented. And there is a general feeling which maybe I would like to transport today, that it's kind of underrepresented on a level which can be, in opinion of many, even dangerous in some sense. And the point is that, it's a completely different approach. It's just, I mean, we have really the feeling that the word simulation is less cool than other word that you can have in the quantum dictionary. And so, and that for this is kind of maybe not so appealing, but really, I mean, we have an object that not only can solve stuff, which other classical cannot solve, and this is already demonstrated. So in some sense, it's extremely important to make a lot of pressure in the direction of miniaturizing, getting more robust object learning, and so the development are amazing. And yes, there is a feeling that this part is dangerously underrepresented.
Great, thanks, Francesca. Crystal, the same question to you. How's the Flagship doing? What adjustments should be made in light of results from around the world, if any?
Yes, we have, of course, a hard competition, as you said, United States, China, and so on. I would say there is a lot of activity in Europe going on, broad activity, so we really cover all fields. And yeah, as Francesca said, we have to go maybe now more in the direction of this miniaturization and so on. So that's more going in the direction of commercializing what we have. Research can help there. This has to be pushed. And I would say we should also maybe at some point focus. So if we look at China, then we see 1 or 2 results: superconducting, optical quantum computers, and that's it. So maybe they are more focusing.
Thanks, Crystal. We're out of time, but maybe just a few words from Readiness at the end.
For the flagship. So
more photonics. That's what I mean.
For photonics.
That would be music to my ears, but sorry,
No, why not? I think it was just that if you see the difference with the US, for example, is that the people who are actually building hardware, they know very well how important applications are, like IBM or Google or Microsoft, right? So I think in Europe, it has gone a little bit, under the radar of how important it is to actually figure out why these machines are useful. And, I think that we need a much stronger collaboration between the computer scientists and the algorithmic experts who are mostly outside the flagship, and the physicists who are actually building the hardware, and also the HPC people that we do need them, because we need to combine everything together. So it is information and communication technologies. So we need the entire stack there, including photonics. Let's not forget other things on the flagship, including communication and having, quantum computers on the server and being able to connect to them. So we need many things, and we need to refocus. And yeah, it would be great if we could get something interesting happening in Europe, and we have everything to succeed. So let's get organized a bit better.
Perfect. All right. Thank you to the panelists and to the organizers. So that's the session closed. We hope you enjoyed the rest of the day and the conference. Thank you.
Thank you.